So we're very happy to have Paul-Konstantin. He's going to tell us about some things about 60 SCFTs. So take it away.
So yeah, let me start by, of course, thanking all the organizers for having this great seminar series and also String Pheno, which I think is really important to keep our community connected. And well, this brings me to the topic of my talk, which is concerned with all kinds of non-simply connected. So it's about non-simply connected symmetries in SUGRA and 60 SCFTs. And this is basically work that I've done together with Nadir Hajju like 6 months ago, and also recently with Marco Stirigel and Fabian Rühle. And I think Fabian is also in the audience. Okay, so what I'm concerned at is the field theory that has a non-simply connected gauge group. So what does it mean? So it means, so I go forward straight with an example. If you have a gauge group SU2, this gauge group admits a center Z2, and representations generically carry charges under them. So, for example, all odd symmetrized representations like the fundamental or the 4, they carry a non-trivial charge, whereas, for example, the adjoint and, well, if you just repeat the pattern, they carry a trivial charge. So now if you eliminate these fields that have a non-trivial charge from your theory, then this theory admits a non-trivial electric one-form symmetry. And I can now gauge by the symmetry. So I can basically divide by that symmetry, ensuring that, of course, all these guys are absent. And then I will get an SU2 mod Z2 theory, which essentially is SU3. So now your new fundamental in that sense is the 3, the adjoint of the SU2. So this is like the main difference, but of course the difference is way more subtle, as Aroni, Zyberg, and Tachikawa showed, namely that theories where you have quotient or unquotiented symmetries or actually have a very different spectrum of Wilson line and 't Hooft surface operators. So now if you just go and take your simply laced Lie groups like SU, SUP, SOs, and so on, and look at the centers, you find that basically all of them have a rather low center, apart from these SU2 guys or these SUP guys here. And this would, of course, immediately trigger the question of anyone who is in the swampland program, oh great, SUP has a ZP center. I can probably divide out by any P, any SUP, but of course, you also know from landscape that there should be a cutoff, and you wonder, what is this cutoff? How high can I actually quotient? And this is basically the question I would like to answer in this talk. And in order to do so, I want to systematically construct superconformal field theories or superconformal, well, or super symmetric quantum field theories and SUGRA theories that have such a non-simply connected gauge group. And I want to be super flexible. So I want to be able to construct all kinds of gauge groups, and I want to do it in a consistent fashion. And I do that in order to use some geometric arguments. Which brings me, of course, to the tool of my choice, which is F-theory, where I'm able to engineer these things all in a consistent fashion using geometry. And of course, I'm very capable of mapping out a vast part of the swampland and being able to post some of these swampland questions into geometric terms. So if I want to engineer a gauge group of ABCDE type, then I, of course, know how to do it. Kodaira tells me how to do it by engineering certain torus fiber singularities. But I also know how to engineer a non-trivial fundamental group for these gauge groups by engineering additional finite points, or actually a non-trivial finite model Weil group, as Aspinwall-Morrison and Meyerhofer, Weigand, and Oscar Till have showed a couple of years ago. So this, of course, interesting also for a couple of other reasons. Mainly, I can also use, of course, the same geometry, put M-theory on it, and then I can just relate F-theory via M-theory duality and engineer these higher form symmetries, as have been also done like very recently by these people here. But I can also use other fun geometric games that I can play with geometries like this. For example, I'm since quite some time, I'm pretty obsessed with the fiber-wise mirror duality of fibrations with non-trivial finite model value group to genus 1 fibrations, and you can also use this shift symmetry in order to construct smooth Calabi-Yau quotients that preserve this vibration. Great, but for today, I want to ask these two questions. So what of these fundamental groups of the gauge group in a SUGRA theory are actually allowed? And I will do so by relating it to geometry. And how does a non-trivial fundamental group for the flavor group in an SCFT impact the structure of the SCFT? So that means that basically my talk is split in these two parts. I will first give you the geometric outline, which will have to do with this finite model value group. Then I will relate that to restricted monodromies and to modular curves. And in the second part, I will try to answer my initial question for SUGRA theories, and then I go to the SCFTs, the third part. So great. So what do we mean by F theory? Of course, we take an elliptically fiber Calabi-Yau threefold or n-fold Y, which I'm able to split everywhere into two pieces, namely a torus, where I've just written the fundamental domain here, and a complex space here, which can be compact or uncompact. The key point, of course, is that if I place a 7-brane, these 7 branes act basically as SL2Z defects for my complex structure of the torus. So if I put this like a single 1,0 brane, this will shift my axial dilaton coupling by an action of T in my SL2Z group. So it will shift T tau by tau plus 1. And this will actually give you an action on this lattice of this torus that you have here. And then I can, of course, just do combinations of the S and T generator of SL2Z and engineer all sorts of branes. So but now I want to ask a little bit of a more sophisticated question. Now I want to take a torus that admits another point of order 2. So here I always have the origin, the 0 point, but now I want to add another point on this elliptic curve. And as Bin has shown in many, or as Bin has the topic, the last couple of years, is that if I have such a point, I will actually have an addition law on the torus, and this addition law will generate me a group, which is the model value group. And if I'm now able to add this point p times to itself, then it's a finite point. Well, sorry, if I add that point p times to itself and I will come out at the origin, then this will be a finite point of order p. And I'm actually always able to put that point in the fundamental domain at tau over p, like at this position here. For example, and here I would have a point of order 2 because I can just add it to itself and then I go down here. It's a point of order 2. And so then, of course, there's a lot of literature that I'm now basically able, if my fibration preserved this order 2 point over the whole geometry, then this model value group law will basically inject into the Laurent-Savary lattice of my resolved Calabi-Yau. And from that, I'm actually able to construct some kind of projector, this so-called torsional Shioda map, which actually projects out all of my non-trivially charged matter fields. So I don't want to go too much into these details because this has been worked out in the literature quite a bit. But I will just take these results and will use the statement that if I'm able to preserve torsion for over the whole base, then I get this projector, and this will effectively give me this quotient structure that I'm looking for. So what I want to discuss today is a little bit of a different perspective, which I personally like a lot. Namely, now I'm asking, so which elements of SL2Z actually will fix the structure of this elliptic curve and this torsion point here? For example, if I put a D7 brane and I have this T transformation that I was discussing before, then the action on my fundamental domain will not leave this order 2 point here invariant, because I go to tau plus 1, and now my order point is in the middle of my fundamental domain, but not at the point here. Actually, the generator that I should consider better that would fix this position or that would leave that position invariant is just taking two of these branes. Then I have a double shift and my torsion point just stays where it is, still on this tau half line. So now I'm asking which generators of SL2Z leave this torsion point here invariant. And this is known in math. So this is a so-called congruent subgroup, like gamma 1p. And these are all gamma matrices, or all matrices in SL2Z that are basically lower diagonal mod p. So this is like a more refined subgroup of SL2Z you can think of. And this is the group that I will now look at. So if you just write down a long list of all brane configurations that you can have that correspond to certain monodromies, you will immediately find that these monodromies are compatible with the congruent subgroups that you are using in order to get this modded structure. For example, an IN fiber has this monodromy matrix, and it is consistent with the gamma 1 and gamma n congruent subgroup, which is consistent with the fact that it has a ZN center, and if I have this torsion point fixed, then I can model the modding that I want basically with these congruent subgroups. And I can, of course, go through all the list of all the other ones and can show explicitly that an SU3 brane leaves a gamma 1,3 congruent subgroup, for example, invariant. Great. So now I have related my question about the fundamental group of my gauge group into a question about what is the highest torsion point I can have in a vibration. So it's a geometric question. I can just look at the math literature, what's known. And it's known, for example, that for a torus over the rationals, the highest order point is Z12. So it's a Z12 point. And for K3s, for example, the highest point I can have is Z8. But actually not so much is known for Calabi-Yau 3 and 4 folds. And that's, of course, a little bit more the case of interest for us, because we want to know things happening in 6 dimensions and in 4 dimensions. So the question that we are having, as posted before, is now really, what is the moduli space of an elliptic vibration in general? And this generic moduli space that you're having is actually very nice encoded in the so-called modular curve. And the modular curve is simply the values of tau that I can have on the upper half plane modded by SL2Z. And this is just this keyhole structure that you have here. And of course, then at infinity, you would also have this additional cusp. And when I'm adding this point at infinity, then I would get basically get my modular curve, which topologically is a P1. Great. So what does this story tell me? It tells me that in this moduli curve, if I fibered my torus over some complex surface or some complex line, then I know that I will always have a cusp, because there is a cusp at infinity. So there will always going to be a point, or I could imagine one locus that hits this cusp, because it's generically there, it's in the generic moduli space, and that there will also be, of course, like points of higher symmetry, like those where F and G vanish. Great. So, but now I'm asking, so what is the generic moduli space of an elliptic curve with a torsion point? Yeah. So as we said, the generic moduli space without a torsion point is just this fundamental domain that I have here, where I take just the upper half plane and I mod by all generators of SL2Z. But now I don't mod by all generators anymore, but those that also leave the torsion point invariant. And this is this congruent subgroup. So I have the smaller quotient here. And actually, the modular curve, or the fundamental from which I can read off the fundamental domain, will now be some kind of tessellation of the fundamental domain of the original modular curve into these subregions here. So now I have these various subregions in my new modular curve. And of course, I can use this to read off what my properties of my generic moduli space are going to be. And the first surprise is that I find that there is an additional cusp in my moduli space. And this additional cusp comes basically every time when these new triangles that I have here from my tessellation, when those triangles all hit each other. And here you see that I have this triangle here and I have that triangle. Since these two sides are identified, I have basically these two triangles that will flow into the origin, and I get a new cusp from these tessellations. And this is here again, sorry, of course, the Z2 example. And this is, of course, equivalent to just concretely construct the Weierstrass model for a Z2 point that is left invariant. So here, this is the Weierstrass model as constructed by Paul-Konstantin and David Morrison that has this additional torsion point at x equals y equals 0. And when I construct the discriminant, I just find that it will have, in addition to the standard I1 cusp, it will precisely have this I2 cusp here that I can read off without all this construction directly from my modular curve. And when these A's here, oh sorry, I think there's an A1 missing here. If these A's are functions on some base because it's a fibration, then I will know for sure that these cusps will always be hit. So this is the basic ingredient that I will use. And of course, in some sense, the physical message of this is that just the structure of the generic moduli space that is encoded in this modular curve will tell me that if I want to have a fundamental group, a non-trivial fundamental group like Z2, I will at least have to have an SU2 gauge group to quotient by. And this is encoded by this cusp that you have here geometrically. So great. This is super cool because now I can just use all these number theory results and construct higher order congruent subgroups and their modular curves and just read off the cusp structure. And what you will see, of course, is that the tessellation becomes more coarse and coarse the more generators or the higher order the generator becomes. So here, for example, I had these additional I2 cusp. If I have a Z3, I have another triangle that flows into my origin. So I have an I3 cusp, which is an additional SU3. But then if you go too high, or if you go much higher, you will actually see that you find multiple cusps. So not only this one cusp that you had before, which in this Z5 example would be an order 5 cusp because you have 1, 2, 3, 4, and 5 triangles that flow into the origin. But you have even more cusp. And this is maybe not super well to see, but here, at this point, you have 1, 2, 3, and then the identification 4, 5. Since these two guys here are identified, you will have another I5 cusp. So if the torsion just gets higher and higher, you will not only introduce one singularity, but you will introduce multiple singularities in your generic fibration. And this is just a property of this congruent subgroup. And of course, I can go even higher, and I start to get more and more of these additional cusp points that I can just read off without even constructing the Weierstrass model. So here I have, for example, 3, and for gamma 1, 9, I would have a Z9 torsion, and I get an SU9 to the 4, minimal gauge group. So this is really the minimal thing you get when you fiber this whole thing over a compact base. So this actually gets me already to my result. So you can really use this congruent subgroups here and the minimal cusp structure you have in the modular curves to put already constraints on all kinds of geometries. For example, if you just have a surface, you already know that you cannot overshoot the Picard group of these surfaces, for example. And that tells you that the rank of your gauge group for a DP9 cannot be higher than 8. And for example, here for Z7, I have already a gauge group rank of rank 16. So that's why for DP9, actually, it already stops here. And the same is true for K3s. So here I know that the maximum gauge group rank cannot be higher than 16. But for example, Z9 has already too high, a rank which is too high, which kicks it out. So here, just from the geometry, you can already write down these constraints. And this is, of course, consistent also with the list of Mirana and Person that have constructed these K3s explicitly. But now the new result for Calabi-Yau 3 and 4 folds is that in general, since these singularities are generically there, they will also generically intersect. And if the torsion is relatively low, like between 4 and 6, for example, you will see that they will all intersect in 4, 6, 12 points, which is not great, but also not super bad, because you can get rid of those guys by a base change, by basically blowing up the intersection points. But if the torsion is high enough, then you will actually find that the vanishing point is of order 8, 12, 24. And it is known that these singularities in codimension 2 do not have a Krepp Calabi-Yau resolution. And this is all information you can just get immediately from the modular curve. But of course, we also satisfied that by explicit construction. And you see that you will always have these points here and we can never get rid of it. So just to put the results like in a handy way, so for Calabi-Yau 3 and 4 folds, we find that the torsion that you have is only that torsion that is also possible in a DP9. And that's, of course, since DP9 has an E8 underlying lattice, is precisely that torsion that embeds into the E8. And this actually also shows that all the torsion models that Espinwall and Morrison have constructed 98 are in fact the most general ones, and they are complete for 3 and 4 folds. So very good. Now let's leave gravity behind and go to super conformal field theories. So this is now a little bit of a change, but now the geometries that I want to construct is actually the one that focuses on such a two-dimensional non-compact base, V2. So I'm considering F theory in 6 dimensions. And my geometry is going to look like this. So it will consist of a bunch of spheres, P1s, that have a certain negative self-intersection N. And these are going to get wrapped by 7 branes that give rise to a gauge algebra G. And this whole configuration is also going to hit by non-compact flavor branes at some ends. So this is the general configuration that you would get. And of course, then at these intersection points, you would have like bifundamental matter of these gauge algebra factors. So now you can, of course, wrap these additional spheres that you have here by the 3 branes. And if they have, if these spheres have a finite volume, then these 3 branes give rise to massive 6-dimensional strings. And the mass or the string tension of those is actually going to go with the volume of these P1s. So if I'm able, which I will assume in the following, if I'm able to contract all these spheres here to a point, possibly singular, then I will also get the limit where all these strings become tensionless and massless, and I will actually engineer my SCFT. And the stuff that I have here is essentially just the tensor branch of the SCFT I have constructed. Of course, there was a lot of work by a lot of people, and I'm pretty sure I'm missing a couple of people here. And yeah, I hope, well, you can complain in the questions later. So now this is the basic setup that I have. And what I basically now want to do is take this whole thing and use the geometry that I had before and constrain my monodromies to these congruent subgroups, yeah, by enforcing an additional torsion points for the whole fibration. Great. So then what you have to do is you have to discuss a couple of your basic building blocks that your SCFT has. One of the main ingredients of those is actually the non-Higgsable clusters, which are just these compact curves that I showed you before with a relatively high negative self-intersection, like starting with 3. And what you then would find is that the generic Weierstrass model will force you to have a generic minimal gauge group onto those guys. But remember, there's no torsion here. This is just the generic stuff you get without any torsion point. You would get, for example, these SU3, SU8, F4, and so on. Now, I do the same thing, and I switch on a preserved torsion point. So then these non-Higgsable clusters would change a little bit. For example, if I had, like a 4 curve, which has an SO8, this is of course compatible with the Z2 torsion that I had, and this actually will not change. So since these gauge groups here are compatible. But SU3 does not have a Z2 center that I can mod by. So what automatically happens in the Weierstrass model is that the gauge group gets enhanced to the next bigger thing that has the compatible center, which is SO7 here. And then you will also get these additional SU2 flavor groups here, which in fact have to do with these additional non-minimal singularities that you can read off from the modular curve that I have told you before. And of course, the story gets worse and worse the higher the negative self-intersection of these spheres become. F4, for example, does not have any center, but you want to have a Z2 torsion and a Z2 quotient. So the gauge group enhances to the next bigger thing, which is E7. And then after resolving the other kind of singularities here then you basically get such a configuration here with a bunch of SU2s and the E7 in the middle. So, but if you would shrink those down, you would get back to this -5 curves. And of course, you can do the same thing with Z3 and all other kind of torsion models that you have. Z3 is of course compatible with the SU3, so that doesn't change. But the SO8 does not have a Z3 center, so it enhances to the E6. And then you get these kind of clusters. So you get, in general, a couple of modified non-Higgsable clusters, if you wish, when you have these torsion points in your geometry. The next building block is going to be the superconformal matter, and that is basically just the case when you have an intersection of two branes, like an SU1 brane and an E8 brane, then such an intersection will actually not lead to a perturbative matter that you would have under the C8, like the fundamental of E8 is perturbatively not allowed in F theory, and it will actually become an SCFT by itself. And when you resolve it, you get just this one curve and no gauge group, but you will have this E8 flavor symmetry, and this is the so-called E-string theory. Now, if I switch on the torsion, I want to enforce again this global quotient. And for Z2, I have now two possibilities. Now, I let it either be SU2 and E7 or SU1 and SO16. And these are actually very nice in one-to-one correspondence by deleting one of these nodes in the affine E8 Dünken diagram. Of course, then you can enhance the whole story more. You can increase the flavor group. And for example, here you would have an unmodded E7 SU2N quotient, flavor group. And the tensor branch of this theory looks like this. So if this flavor group here that you have has actually a Z2 center, because you have a Z2 here and a Z2 is there, and you want to mod by. But due to this tensor branch, you're actually not allowed to do so, because you have matter here that breaks this torsion group. You have SU odd factors and also hypermultiplets that will not allow you to mod by this group. But if you realize the same flavor algebra, but with a different group structure in our torsion model, then you will actually see that everything is now consistent and you have quite a different tensor branch structure. Now only SU even gauge group factors are allowed, and of course also all the matter factors are consistent, and the whole geometry is just consistent by itself. And this is just a nice example where you see how the flavor group and algebra can differ when you mod by the C2 factor. Of course, you can do this now with all kinds of different quotient factors. You can now engineer like interesting theories that also have interesting like higher anti-symmetrized matter in your geometry, or higher order torsion, where now the C6 factor just acts with a subgroup on the different flavor factors, or also you can of course engineer multiple torsion groups at the same time, and you get like all kinds of funny geometries. Okay, so this actually brings me already to my conclusion. So elliptic fibrations with an additional torsion point lead to symmetry groups that are non-simply connected. And in this work, we have actually shown how these order P points will lead to restricted monodromies that lie in a congruent subgroup, or some generalizations thereof. This will in fact lead, as you can just view from the modular curve, to additional enforced singularities. And and it can happen that these enforced singularities just make your geometry not Calabi-Yau because they are just too bad, essentially. And the swampland criterion you can extract from this criterion is that for Calabi-Yau 3 and 4 folds, you always want to have a group that somehow embeds into E8, but not higher. The same approach we can now use for SCFTs to construct interesting non-simply connected flavor groups that I basically just mentioned. Okay, but this brings me to my conclusion. Thank you.
Great. Thanks a lot, Paul, for the very nice talk. Let us all clap using the Zoom reaction feature. We have a few questions already in the chat. The first is from Cody.
Okay.
Hey, Paul, thanks for the very nice talk. So my question is, so you mentioned, it's on the last slide here too, I think, that the cutoff for the Calabi-Yau threefold and fourfold case is due to non-Crepin resolvable singularities.
That's correct.
But no, in many contexts, these don't really bother us, the terminal singularities, as long as they're finite distance and moduli space. Is it
Right.
the finite distance that you're worried about for some of
No,
these?
those are not at finite distance.
Oh, so yeah, okay. So there are the terminal ones that are finite distance, but these are the ones that are not. Okay.
Yeah, these are just very bad. These are, yeah, those will completely break your Calabi-Yau. You cannot, and they are just enforced by your geometry. You cannot, well, you can basically not get rid of them, but keeping this torsion. Yeah.
Got it. Thanks.
Great. Let's see. Miguel has a question.
Yes, so thanks, Paul. That was a very nice talk. And my question is actually related to Cody's only. I am more ignorant about the theories. It's probably more elementary. So I mean, all of these constraints that you get, all these swampland criterions, just how much is supersymmetry an ingredient? Like if I don't, if I just have any space with an elliptic vibration, not necessarily with a complex structure or whatever, then do you expect these constraints to also hold, or maybe I can engineer more stuff? Is that what happens with these non-Crepin singularities, that there's just no way to make the whole thing supersymmetric?
Good. So this non-Crepin singularity in some sense tells you a couple of things. So I mean, first of all, I should of course say that, I mean, this whole construction is like with F theory in mind. Yeah, maybe there is some way to engineer non-simply connected gauge groups in some other way. And of course, I mean, this is something we get from the geometry, and I have F theory in mind.
Right. No, but so I'm thinking, so F theory basically tells you that there's like a torus fiber over the compactification space, right? But when you use things like the Kodaira classification or whatever, you're actually assuming that the whole thing has a complex structure and whatnot, right? So that is kind of like, that is given to you by supersymmetry. So could you relax this?
I would not know how to then argue for something like this. I'm also not sure which kind of singularities would be allowed then. And in some sense, also this Crepin singularity that you would have, I mean, yeah, it would break the Calabi-Yau condition. So it would break your supersymmetry. Right. But so if you don't care for that, possibly more goes.
Okay, and just a related question. So have you thought what all of this implies? So let's assume the supersymmetry. What does this imply for the standard model gauge group? Can you rule out some global forms of it?
Very good. So this, thanks for asking. This brings me to like a small caveat that I also have on my slide, but of course I forgot to say. So all the stuff that we are saying here is that the group we are modding by is purely non-abelian. So we don't have a U1. As standard model. And for example, in the U1 case, then this kind of non-simply connected structure comes because the U1 mixes non-trivially with your SU2 and SU3. But this is not the structure we're looking at here. Yeah.
Okay, cool. But so could you, so for instance, yeah, I guess all the global forms they involve the U1 quotient. Okay, thanks.
Great. And Yinan?
Hi, Paul. A question about the non-minimal case. We have a coordination 2 for 612. Yeah. So that's in your slides. That's like a Z. For example, you have a Z5 torsion.
Right.
So in that case, have you checked that if you have some kind of strongly coupled matter localized on this coordination loci, then the charge of this thing is like trivial under that like D5 center? Have you
Right.
tried that?
Yeah, this is actually, in some sense, that's a very nice question. And this is also like a point that connects it in some sense to the super conformal story. So for the Z5 case, and also all these higher cases, these of course will be this 4, 6, 12 intersection point that you are having are basically really, yeah, the E-string theories that you are having. But the E8 is broken to SU5 times SU5 mod Z5. And like an example of this is precisely as I have it here in this picture. So in that case, for the Z5, this would precisely correspond into deleting that node here where you have broken your E8 group, and then you have your SU5 and the other SU5 here. But I mean, to say it like this, we have not really computed the charges, but you can see that the 4, 6, 12 is essentially your E-string theory. And that is broken by this torsion. Yeah.
Okay, I see. So in the tensor branch, you already have this SU5 times SU5 mod C5.
Yeah, as a flavor group, yeah.
Yeah.
Right.
And I think we have time for one more question. Lakshya?
Yeah, so you can predict these quotients by using the tensor branch gauge theory. Is there any example where gauge theory predicts a quotient, but you don't see it geometrically?
Let me think if I can think of an example. Not that I know of. Not that I know of. But yeah, I don't know any example now. I mean, sometimes it's of course a little bit tricky to really see how the geometry and the field theory really come together. I mean, how the embedding of this quotient really is and how it's realized in the geometry. But I'm just not aware of a case right now. But this can just take 5 minutes, then I can maybe come up with one.
So in the case when there are multiple Z2 quotients allowed, can you see all possible combinations of those Z2s, or you only see some diagonal one?
Good. So I mean, I should also say in the construction that we did, and also in the paper, we are not 100% exhaustive. Yeah, we constructed a lot, but not everything that goes. So I would not. So in that sense, I cannot answer your question. So
I mean, in a particular example, are you able to construct all the combinations?
Yeah, I think, yeah, we didn't try, but I think it would be an interesting question to see if there's one or a couple of things that the geometry might miss. Yeah.
I see. Thank you.
Sure.
Great. Well, let's again use our very high-powered clapping technology to thank Paul for his excellent talk. There's a few announcements that I want to make. If you look in the chat, I am linking to the String Pheno Seminars website, a very nice website designed by Cody, and I also helped a bit. You can find a schedule. You'll see that next week we are skipping because of Strings 2020, and we're resuming the following Tuesday, July 7th, with Naomi Gendler and Marcus Dayriegel. So you'll also find that in the past talks section, there are slides and links to videos on YouTube of the past talks that we've had, and we'll try and keep this updated throughout the entire series. So with that, thanks again for coming, and let's thank our speakers once more, and have a nice week.